Hello everyone, my name is Tu, and today I will be presenting our work on a simple and efficient hardware implementation of the number theoretic transform for CRYSTALS-Kyber post-quantum cryptography. So here is our table of content. We will go into the introduction, the background, the proposed design, the results and comparison to the previous work, the conclusion, and the reference. So the first one is the introduction. So our paper focuses on designing a fast and efficient hardware architecture for the number theoretic transform, the entity, and the entity is a crucial arithmetic component in CRYSTALS-Kyber design. And the CRYSTALS-Kyber is recently selected as the lattice-based crypto system standard by the NIST, the National Institute of Standards and Technology. And with the entity-based polynomial multiplication, it helps to reduce the computational complexity. And our paper will present an efficient hardware implementation for the entity and the inverse entity operation for CRYSTALS-Kyber. So here is a little bit about the background and the polynomial multiplication, as I mentioned earlier, is a fundamental operation in encryption and lattice-based cryptography, but it can be time-consuming. So by using the entity algorithm and the inverse entity algorithm here, we can reduce the complexity from n squared when we use the traditional method and down to the n by log n when we use the entity-based method. So here is our proposed design. So it includes the two processing elements here. So you can see the entity2 input here or entity2 point. So we have two of that for parallel computation. And we also design a Montgomery reduction unit for the modulo reduction operation. And we design an address generator for in charge of efficient memory access management to optimize the runtime and the latency when we store and when we read the data. So let's talk about our polynomial multiplier. So it involves two blocks. The first one is the DSP-based integer multiplier. And the second one we need is the word level Montgomery modulo reduction unit. So we need it to reduce the 24-bit product from the integer multiplier to the 12-bit product modulo Q. And for the Montgomery modular reduction algorithm, the word size that we choose is 8 because it is suitable for Kyber. So that is why we need two modular reduction subunit here for the operation to work. So as I just mentioned, it is a word size that we choose and this figure here. So our implementation for the Montgomery reduction units based on the algorithm for you can see down here. So after we implement the modulo multiplier, we will use it here to implement the butterfly unit. And the butterfly unit is the main processing element for the entity to input operation. So it will take the input as the one fiddle factor and two input coefficient and generate two output coefficient, one for odd index and one for even index. So you can see here is a hardware implementation for the entity and invert entity algorithm here. So since we only use two entity, two block, so we need to control the memory efficiently to reduce them. So that is why we design the address generator. So our address generator had three main states. The first state is the idle state, the second one is the entity, and the third one is the wait state. So in the entity state, it will generate the read address for the input coefficient and the read address for the corresponding fiddle factor for the input for the entity block. And after the entity block generates the output coefficient, it will generate the write address so that we can store the output coefficient to the DRAM, and after that we will use as the input for the next entity state operation. Because we need to iterate multiple entity state, we need a wait state between it. Because it is used for the DRAM read and write operation, we need to wait for it. And for CRYSTALS-Kyber, we need to do 128 point entity operation. So the entity state need to be iterated 7 times so that we can get the final entity results. And from our testing, we can see that with the address generator, it helps to reduce the operating time and the latency significantly. So here is our results. So let's talk about the FPGA. So in the FPGA, we choose to implement on the Xilinx ATIC 7. And the table 2 here showing the result for the synthesis and implementation on FPGA. So you can see the frequency we got is 102 MHz. And we utilize the DSP block and the DRAM block so that we can reduce the number of lookup table and the flip-flop that we use. And for the ASIC one, so we use the TFMC 65 nanometer technology 5, and we got a very high speed frequency here is at 497 megahertz. And here is our area report. So let's go to the comparison with the previous work. So the table here shows the comparison. So let's look at the FPGA result first. So you can see because we utilize the DSP for the integer multiplier, we reduce the lookup table, the number of lookup table and the flip-flop that we use. That's why when we compare it to work number 9 or work number 10, they don't have the balance in the FPGA results. For example, like because we use the DSP and the DRAM, we reduce our use of the lookup table and flip-flop. Whereas you can see in number 9, the lookup table that they use is very high. Or you can see in work number 10, they don't even utilize the DSP and the DRAM of the FPGA. So let's talk about the performance. So our frequency is 102 megahertz. So it's quite middle here to compare to other work but it's still higher than the work 11. And let's talk about the operating time and the latency. So our design have very small latency of about 600 cycle for the entity operation and 800 cycle for the invert entity operation, and it's smaller compared to the work in 11 and the work in 9 and the work in the 10. So why we have the small latency? That is because we use the address generator to generating the write and read address efficiently to access the memory. So conclusion, we achieve a lower latency and better resource optimization with a mid to high performance, making it suitable for real-world application on FPGA. So let's talk about our research in the ASIC side. So this is a table of comparison. So when we look at the frequency, you can see that our design frequency is very high. This is 497 MHz and is outperforming all the previous work. And when we look at the entity latency, so it is very small compared to the work in 7 and the work in 6. This is due to our address generator scheme that we use to read-write the memory. And when we compare to the gate count, so our design gate count is bigger than the work in 7 and 6, but when we refer it to our very high performance, we think that this is reasonable trade-off between the area and timing property. So as a conclusion, so our design significantly outperforms the prior implementation in terms of speed and resource efficiency, so making it a promising candidate for high-speed security hardware implementation. So here is the conclusion part. So we propose an efficient entity hardware architecture for the CRYSTAL-Kyber, achieving low latency and high performance on both the FPGA and ASIC platform. So on the FPGA, our design provide a middle high performance and a very optimized and balanced resource. And on the ASIC, um, it achieves very high performance, making it suitable for high-speed application. And our study demonstrates the potential of efficient hardware implementation for post-quantum cryptography. And especially is the CRYSTAL-Kyber. So finally, I would like to acknowledge the reference that we use in our work list is here, and thank you all for your attention and listening. Goodbye.